So let's finish up what we were doing in class. We worked on partial fraction decomposition, but we ran out of time to actually do a complete integral using this idea of partial fractions. So let's go ahead and do a couple examples with that. So in class we had been working on the integral of x minus 13 over 2x squared minus 7x plus 3. And we had just started to take the integral of that. When we did our partial fraction decomposition, we ended up getting A turned out to be, let's see, 5, and B was negative 2. So we could rewrite this integral as 5 over 2x minus 1 minus 2 over x minus 3. Okay, and then those are integrals that we can go ahead and go ahead and solve, take the integral of them. So on this first one, we let u be 2x minus 1. So then du was 2 dx, and we let dx be du over 2. And then on the second one, we really don't have to do a u substitution. That would just be the integral of 2 times 1 over x minus 3 dx, which is just going to be an ln problem. So let's go ahead and work this all out. So that first one, we end up with 5 halves, the integral of 1 over u du, minus, and then the second one was 2, the integral of 1 over x minus 3. And again, if you want to make that be a u substitution, you can, and you would let u be x minus 3, so it's of the form 1 over u as well. All right, so then this integral equals 5 halves, the ln of u, and don't forget your absolute values, minus 2 ln absolute value of x minus 3 plus c. So we get, substituting back in, 5 halves, the ln of the absolute value of, and then we got to go back in and substitute what our u was. So that's 2x minus 1 minus 2 ln of x minus 3 plus c. And then you can leave it like that and be done. But if you're on a multiple choice question or you're in the book, they're going to end up using log rules to rewrite this. So they're actually going to end up with equals the ln. And because we have subtraction in between our two ln's, it'll turn into a division problem, as well as our coefficients will end up becoming the exponents of our logs. So what we'll end up with is the ln of 2x minus 1 quantity, 5 halves, over x minus 3, well, so much for the 3, I made it be a 1, x minus 3 squared. Now, the question is, do we need absolute values on this? And we are taking the square root in the top, which would turn it to be positive. We are squaring the bottom, which would be positive. I would prefer to see absolute values up here so that we could, in fact, take the square root of that. But otherwise, you don't necessarily need them over the whole expression. And then don't forget your plus c. All right, so now let's work another example, add a little bit to this. Now we want to find the integral of 3x to the fourth plus 1 divided by x squared minus 1. When we are looking at problems like this, you don't just jump right into partial fractions. Of course, you go through your toolbox and pull out all those other things you already know. You know, are there any rules that I know that apply? Not really. Can I do this as u substitution? No, because neither of these is the derivative of the other piece. Can I do integration by parts? No, this isn't the right type of problem for that. So now we start looking at, well, maybe I have to do it partial fractions. I can factor the bottom. X squared minus 1 is going to be x plus 1, x minus 1. But the problem here is that the numerator's exponent is higher than the denominator's exponent. And we have to have the degree of the numerator be less than the degree of the denominator in order to do partial fractions. So before I can integrate this using partial fractions, I'm going to have to do some division in order to get the numerator's degree smaller than the denominator's degree. So I'm going to come in and I'm going to write my denominator on the outside, and then I'm going to write my numerator. And since I have so many missing pieces in here, I go from an x to the fourth down to a constant. I'm going to leave myself a gap just to make sure, because I'm going to end up having to fit some pieces in there. So I'm not sure how much room I need, but we'll find out. All right, so I ask myself then, what do I have to multiply x squared by to get 3x to the fourth? And so that's going to be 3x squared. And then I multiply. So 3x squared times 3x squared is 3x to the fourth. And 3x squared minus 1 would be minus 3x squared. But then, as with regular division, I have to subtract. So 3x to the fourth go to 0. And then this would be 0x squared minus 3x squared. But it's minus 3x squared. So it's going to be a positive 3x squared. And then I'm just going to bring down my plus 1. What do I multiply x squared by to get 3x squared? And that would be plus 3, a positive 3. So I'll end up with 3x squared minus 3. But I have to subtract. So that becomes 0. And I'll have 1 minus negative 3, which is positive 3. I'm sorry, I didn't add them. Let's try that again. 1 minus negative 3 would be 1 plus 3, which would be 4. A little elementary math mistake there. So this is our remainder. Okay, so we write this as plus 4 over x squared minus 1. And now we have a fraction whose numerator is a degree less than the denominator. And so we can now do that with partial fractions. So I'm going to rewrite my integral up here as the integral of 3x squared plus 3 plus 4 over x squared minus 1 dx. And I can integrate the 3x squared and the 3 like normal, and then I would use the 4, or I would use partial fractions then to integrate the 4 over x squared minus 1. So we've got equals, the integral of 3x squared is just x cubed, plus the integral of 3 is just 3x, plus the integral of 4 over, and instead of writing x squared minus 1, I'm going to go ahead and write it in its factored form. So x squared minus 1, x minus 1, x plus 1. And oops, don't forget your dx. Okay. And then we're going to use partial fractions to find out how I can break that up, because this would be x cubed plus 3x plus the integral of a over x minus 1 plus b over x plus 1 dx. All right. So then what I know is that 4 is going to equal a times x plus 1, because remember I'm going to take the coefficient or the numerator of one of the fractions and write it times the other one, plus b times x minus 1. And I do that because that's the process we would go through to get a common denominator in order to be able to add those. All right, so when is the first term going to go to 0? When x equals negative 1, we'd have 4 equals, and that would be 0 plus b. Sorry, I didn't write my negative sign in there. Let me try this again. Equals, when x equals negative 1, and so that would be -1 minus 1. So we'd have 4 equals -2b, and b equals -2. All right, and then we have when x equals +1, that would make the last term be 0. So 4 will equal a times 1 plus 1 plus 0. And so a is going to be +2. So we go back to what our work from before, and we'll have x cubed plus 3x plus the integral of 2 over x minus 1 plus -2 over x plus 1 dx. And those are integrals that we can go ahead and take fairly easily. They are going to be ln's, so we would end up with x cubed plus 3x plus 2 times the ln of the absolute value of x minus 1 minus 2 times the ln of the absolute value of x plus 1 plus c. I ran out of room there. And of course your book, multiple choice, AP, all of that is going to end up writing your answer as x cubed plus 3x plus the ln of, and you could leave that 2 outside. It does go to the into the exponent. I'm going to leave it outside just for right now since both terms have a 2, and I'm going to write it as the absolute value of x minus 1 over x plus 1 plus c, but you could also write that as x cubed plus 3x plus the ln of x minus 1 over x plus 1 quantity squared. And I completely ran out of room thanks to that c. So let me just write that as a squared and then plus c. Sorry for running out of room. Okay, so long ways to get to the answer, but that's how you would use partial fractions when you have the case of the numerator's degree being higher than the denominator's degree. In this problem, we want to find the general solution to the differential equation dy dx equals 6x squared minus 8x minus 4 over x squared minus 4 times x minus 1. So we're going to do this again with partial fractions, and let's see how this works. So we're going to write the integral. Y equals the integral of 6x squared minus 8x minus 4 over x squared minus 4 x minus 1 dx. And the thing to take note of here is that we have this x squared minus 4, which is not linear. And as I told you in class, we were just going to be working on ones that were linear. So this is one that needs to be factored further. Okay, so we're going to say this equals the integral of 6x squared minus 8x minus 4 over, and this is going to be x minus 2, x plus 2, and x minus 1. So we have 3 factors in our denominator this time instead of only 2 factors. But it still works pretty much the same way, because what happens is this is going to create 3 separate fractions instead of just 2, and so we'll have to multiply each letter by 2 terms instead of just 1. So we'll have a over x minus 2 plus b over x plus 2 plus c over x minus 1 and dx. Okay, so when I have a over x minus 2 and I'm trying to get a common denominator, I would have to multiply a by both of the other 2 denominators. And the same way would b, and the same way with c. And when we do that, that should equal our original numerator, which is 6x squared minus 8x minus 4. And now everything's going to work the same. The process will be the same. We'll just find the value that makes each term equal to 0. So let's go ahead and start with what will make the a term drop out. Well, either a 2, negative 2, or a positive 1. And so it doesn't matter which one you choose. Let's go ahead and do when x equals negative 2, just since that term comes first. Okay, so make sure you plug negative 2 into everything. So we'll have 6 times negative 2 squared minus 8 times negative 2 minus 4 equals a goes to 0 plus b, and that will be b times negative 4 times negative 3 plus c, but look, when I plug negative 2 in, it's going to make this last part 0. So that's going to drop out also, and that's really nice. Okay, so when we work all of this math out and combine all of our terms and do our arithmetic, then we're going to end up with b equals 3. Okay, so then I would come and I would look at b, and I would say, well, what number would make b go to 0 in either a 2 or a positive 1? And again, I'm going to choose 2 only because that's just what will make the first one go to 0. It does not matter. You could do either one. You'll get the same answer. Okay, so then we'll have 6 times 2 squared minus 8 times 2 minus 4 equals, and then the first term, that would be a times 4 times 1 plus, and the b term will go to 0, plus, and then look, when we plug in 2, c will go to 0 also. So this is really nice because each term will end up canceling out. When you choose the right x value, it'll cancel out the other two terms. Okay, and so when we do the arithmetic here, we're going to end up with a will be equal to, excuse me, equal to 1. Okay, and then our last one, I'm going to let x equal 1, and this is going to cause us to have only c left because I need c to still be around, and the 2 and the negative 2 made it go away. So I'm going to look and I'm going to choose 1, which makes both a and b go to 0 because of the x minus 1 term. So then I'll have 6 minus 8 minus 4 equals 0 plus 0 plus c times negative 1 times 3. And so then c will equal 2. So then what we'll end up with in our integral is we'll end up with this equals the integral of 1 over x minus 2 plus 3 over x plus 2 plus 2 over x minus 1 dx. And now we have integrals that we can evaluate easily. These all end up being ln's. And so we're going to end up with the ln of the absolute value of x minus 2 plus 3 times the ln of x plus 2 plus 2 times the ln. Oops, I put the absolute value first. Silly me. 2 times the ln of x minus 1 plus c. And then you could, of course, clean that up. Now these have pluses in the middle, so these are going to be multiplication. So I'm going to come and I'm going to write it down here. So that equals, so we're going to have the ln of parentheses, and it's going to be the absolute value of x minus 2 times the absolute value of x plus 2 cubed, and I am going to keep that absolute value on there because that would make it possible for it to be negative, and so I definitely want the absolute value on there. Plus, I'm sorry, not plus, times, and then the absolute value of x minus 1 is going to be squared, so you could actually take that absolute value off if you wanted to. You could leave it on. It's not going to hurt anything if you do, but it shows some evaluation knowledge when you know when to take it off. But it doesn't matter either way. So let me try writing this again where it'll fit. X minus squared, big plus c. All right. So there you've got that integral has been, or that differential equation has been evaluated. That is the general solution. All right, let's look at one more. So now we want to look at one that looks like this. So we have the integral of 6 over x squared plus 4 dx. And your inclination is to come in and to try to make this be partial fractions. But I cannot factor x squared plus 4. And so I can't use my partial fractions because I can't get it into two linear terms. But there is a rule that we have, and it talks about taking the integral of 1 over u squared plus a squared du, and this is going to equal 1 over a times arctan, and I'm going to write that as tan to the negative 1 of u over a plus c. So this is one of your integral rules. So if you don't remember this, you need to go back and review these. There's a really nice table in your blue book, and it should be posted up on Blackboard as well. So I come in and I just tell myself, what does u equal and what does a equal, and then I just use my formula. Now, of course, that 6 is just a constant, so I'm going to rewrite this as 6, and then du would be just the same thing as dx in this case. So I'm going to write this as u squared plus 2 squared, and I know that that's going to equal 6 times 1 over a arctan. And you could write it, I started to write it as arctan, or you could write it as tan negative 1. Either one is fine. And then u is just x over a plus c, and we clean it up, and so we'd have 3 tan inverse x over 2 plus c. And just don't let it confuse you that I switched back and forth. I just want to remind you that arctan and tan inverse are the same. So this is a problem that looks like it would be a partial fractions, but it's not. In this case, it's not because it can't factor into those terms that are linear factors. So since it doesn't factor, then it won't. And then just remember that you can always divide if the numerator's degree is higher than the denominator's degree. And also don't forget that something that looks like a u substitution problem might actually be, that looks like a partial fractions problem might actually be a u substitution problem. For example, one that looks like the integral of, let me make this be a 6. The integral of 6x over 3x squared, minus 3. So that is actually a u substitution problem. Let u be 3x squared minus 3, and du would be 6x, and then you could just go from there. So, just keep a sharp eye out. Not everything that looks like it could be partial fractions will. So try your other rules first before you try partial fractions. Okay? All right, so try the problems that I've assigned and just let me know what questions you have.